So now I hope you're convinced that Bayesian phylogenetic inference makes sense from a theoretical point of view. Let's now focus on divergence time estimation. So we all agree that we want something nice like this, right? So we want a tree that has some branch lengths calibrated to geological time with some interval, and by the way, a little bit of promotion. This paper is from Mike and Carl and all their collaborators. And it's actually a very nice paper because besides working with this really cool group of plants that are the Maratialis ferns, they give a lot of practical and technical advice on how to run this kind of analysis. So it would be like a really good starting point for you to go and check details about how to run this type of analysis. Oh, I have a bunch of links on the tutorial. It's inferring the total evidence timescale of Maratialian fern evolution in the face of model sensitivity. But the link is there, so you'll see it. Okay, so what is the problem with dating? Walk through why it is really hard, right? So when we are making an inference of a tree, like in the left where we have, it's unrooted, so we haven't specified the root or rooted, it doesn't matter. We usually get the branch lengths in terms of number of expected substitution per sites, right? Let's call it V, like it's specified there. So the problem is that from my analysis, this is what I get, the number of expected substitutions. Let's think about molecular data. So these many 5 substitutions in one branch, 10 in the other. But V is a function of 2 parameters, right? It's a function of the rate at which the characters change, how fast they change, but also how much time has passed, right? And when I'm dating a phylogeny, what I really want to know, let's keep working about this problem. So the problem is that for a given branch, imagine whichever branch, I can find a value of R and T of speed and time, rate and time, that make that value true. But I could also find another pair of values, right? I could double the rate and half the time, and I would get the same branch length. And not only 2 values, I can actually get a bunch of values that would have the same branch length, right? So this is what we call the non-identifiability of rate and time. So basically, character data don't have information by themselves about rate and time. Yes, question.
So when you say substitution, then I understand it's not protein or DNA substitution is straightforward. How do you see substitutions in possible?
So it would be the same for morphological data. Oh, there's a question about what does a rate mean for morphological data? And it's the same. So how many morphological changes do I expect in a branch for a given, for a given branch, right? We're gonna talk a little bit about that, but that depends on the model of morphological change, right? But it's similar, it's analogous to the molecular change. What was I saying? So data, rate and time are conflated by trade data. We cannot really disentangle them. So how does being a Bayesian well, it helps us in that we can use the fact that we can set priors to separate these two, separate rate and separate time. So that's the first step. I want to separate them. In practical terms, this means that I have to set a model of how rates are in my tree and a model of how time works in my phylogeny, right? So not only we have to specify a model, but because we're using the Bayes theorem, we can place priors, which is not necessarily bad because we have information from a lot of things, right, that we can use. Yeah, so rate and time. So basically the two models that do this are the clock model and the time tree model, the famous fossilized bird death that we're gonna use today, right? So I separate these two by using these two models connected to the morphological change or molecular, right? Let's just see an example of how this could work. So the easiest or the simplest actually model would be to assume that the rate is constant. So all the changes occur at the same rate in my alignment, for example. That's what we call the global clock model. So basically, if I make this value a constant, right, then I say that the branch length is proportional to time. And if I know this, I can calculate the time. Does that make sense? But that's oversimplified. We don't expect all the markers to change at the same rate, right? So when we're doing divergence time estimation, we really need to develop better models than the absolute clock, which there are. What we want to achieve by using better models is to account for variation in the rates across lineages. So some lineages will move fast, will change fast, some will change slower. And we also want to accommodate using temporal data, right? Because even if I get the global clock, even if I get the proportion, I still need some absolute time to say like this is 100 million years old, right? And that can only come from fossils, okay? Just a little side here is that we can use other things like geological splits, islands, things like that, but let's focus. How are we doing? Good? Okay. Online, are we doing good? Cool. So let's review quickly these two. Today's tutorial will be about tip dating. But in order to understand tip dating, let's compare it with the approach of node dating, which was the first one that we started using as a community. So as the name suggests, node dating uses the fossils in nodes. So let's say I have a phylogeny that I estimated, right? And the branches are in number of substitutions, expected substitutions per number of expected substitutions, yes. I want to get those branches in time now, right? The way we usually do it is when we have a fossil, we think we can do that. So let's say I have my phylogeny, and then let's say I found a fossil and I know the age for that fossil, right? What we would do in the node dating approach is that we would try to place that fossil in a group, right? So here we have a flowering plant, and then we have the clade of the flowering plant. So we would think that the fossil goes on that clade, right? The next thing, and that one thing that can be confusing, is where I'm going to place that fossil. I have to place it in a node, right? But I'm not going to place it in the node that connects the angiosperms. because this fossil could actually be anywhere along the branch that leads to angiosperms, right? On this node, this blue node. Is that clear? Okay. And in practical terms, what we do is that we set up distributions, right? Because of course, the fact that I have the fossil there in the Jurassic doesn't mean that the Jurassic is the time where that lineage appeared. We actually know through the fossil record that probably took a bunch of time since the first angiosperm appeared till it got like those traits that differentiate them from other groups, until they were like widespread enough that they would leave a fossil, okay? So we have reasons to think that actually the origin time for this lineage is previous to when we find the fossil, right? So we have different ways this kind of distributions, and you can check a lot of the papers by Charles Marshall. He has actually a very recent review on that, 2019 or 20, something like that. So we place the distribution, we run our analysis, and our analysis is going to try different values in this distribution, right? And eventually it's going to find one value, okay? But this node dating approach has a series of drawbacks. So the first one is that we have to be pretty sure of where we were going to place that fossil, because that's going to influence our estimates, right? So we need to assign the fossil to a node. We also need to use only the oldest fossil, because what if I had like different fossils that could be along this branch? I just want to use the oldest, right? And based on morphological traits, of course, and on what one person think of what are the characters that define the group, right? So it's kind of subjective. It assumes some morphological evolution. So we place a flower there, but what about the leaves, right? Were leaves more important than flowers? So there's assumptions about the morphological evolution. And all of this is going to affect our estimates. This is like only conflated or like increased by the fact that the model is not non-identifiable from only trait data. So the whole estimation depends only on our fossils. Yeah, I say that. So basically, if you think about this and thinking about to make that prior explicit. So it makes sense first to analyze it in the context of Bayesian rather than penalize maximum likelihood. It makes sense to use Bayesian, and it makes sense to make those prior explicits. So that is what tip dating does, right? So we use the fossils as tips rather than putting them on nodes. All the problems I mentioned are solved by tip dating. So the problem of where does the fossil go is inferred from the data. How old is the node is also inferred from the data. And what if I have multiple fossils? No problem. I can put all of them in my analysis. Does that make sense? So I hope at this point you're convinced that tip dating is a good approach. Let's focus on a particular type of tip dating that is called as total evidence dating, or TED. The fact that we use all the information we have morphology, we have molecular, and we have fossils. One thing to keep in mind is that using total evidence dating can also help us resolve the phylogenies better. Let's say I have this group in orange and this group in orange down here. And let's say that they are similar. If I use a different, like if I were to use node dating, I probably would be tempted to put this fossil here, right? But the age of a group also carries information about the relationships. Because if my analysis is estimating everything at the same time, it will see that the age of this group is very old compared to the age of this group. So that's gonna prevent, or it's gonna have a high cost of putting this group with this group if the age doesn't match. Have information about the position of a fossil in the phylogeny, right? I just went through without the arrows, whatever. Okay, questions? Because now we're gonna get to the model itself.